TRAX, Tracking in Complex Sensor Systems.
Hello, my name is Parinaz. This presentation is about joint antenna and propagation model parameter estimation using RSS measurements. The contribution of this work has been published in the Information Conference on Information Fusion in Washington, D.C., 2015. Hi, I'm Parinaz Kasebzadeh. I'm an early stage researcher at Linköping University working on TRAX project. Here is the outline of this presentation. First, I will provide some words about the motivation of this work. Then I will go through the contribution. After that, the RSS measurement model will be introduced. The next step is estimating joint path loss and antenna parameters. Then I give some results for simulated data. Next step is experimental environments. First, I will talk about the challenges in the experimental environments. Then I will represent the result for the experimental environments. At the end, I will wrap up the whole contribution in few sentences. Let's start with the motivation. Position radio measurements such as RSS enables an operator to identify where issues such as poor coverage or excessive interference are located, which is an improvement strategy for predicting cellular radio network coverage. In conventional approaches, log distance dependent path loss model used for coverage prediction, while directional antenna gain pattern used is generally overlooked. So we propose to estimate jointly the path loss and antenna gain model parameters. In this contribution, first we introduce a semi-empirical propagation model for the RSS measurement, which is a combination of an empirical distance-dependent path loss model with a deterministic antenna gain model. Then a least square estimator is proposed to estimate jointly the path loss and antenna gain model parameters. At the end, the approach is verified in both simulation and real data. Now I want to represent the RSS measurement model. The semi-empirical propagation model for the RSS measurement is illustrated by the first formula, which is a combination of the empirical distance-dependent propagation loss model and the deterministic antenna gain model. As you can see, the antenna gain is represented by the adding horizontal and vertical antenna gain together. Here is the horizontal antenna gain model. Gmax denotes the maximum antenna gain in dB high. Phi is between minus pi to pi, which is the antenna azimuth angle. Phi h is the antenna's horizontal bandwidth in degree. Phi 0 is the antenna broadside angle. GH mean denotes the front to back ratio measured in dBm. This is an illustration of the horizontal antenna gain model together with the real data from an antenna. The parameterized model is a representation of measurements which are in a main loop. Here is the vertical antenna gain model. Psi is between minus 90 degree to 90 degree, which is the negative antenna elevation angle related to the horizontal plane. Psi tilt is the electrical antenna down tilt. Psi v is the antenna half power beamwidth in the vertical direction. G of v mean is the side loop level in dBm of the vertical pattern. Now it's time to introduce the joint path loss and antenna parameters estimation. One issue with the joint parameters estimation is that the antenna gain is modeled different inside and outside the main loop, using mean and max functions, which result in nonlinear equations. Under the assumption that the main loop components are dominant, the contribution of the antenna gain simplifies to this equation. With this simplification, maximum likelihood estimate of the parameters becomes tractable. Here is the estimation results for simulation data. As you can see, by increasing the number of measurements, the accuracy of estimation has been increased. A is the reference path loss, and B is path loss exponent. Phi, as introduced earlier, is the antenna horizontal bandwidth, and psi is the antenna half-power bandwidth in the vertical direction. Sigma is the standard deviation. For comparison purposes, we have also included the path loss slope when the estimator is only estimating the path loss parameters. For example, antenna gain is equal to 0 in the estimator model. In this case, we have a model mismatch and the path loss slope follows the trend of the RSS measurements as expected. It is now also observed that the error standard deviation is much larger, which is due to compensation of unmodeled antenna gain variations. The benefit of adopting a joint antenna propagation model in comparison to only a propagation model is this evident. Now let's move to experimental environments. A rural area is selected for collecting the measurement, and we have used an Android app for logging the GPS position and received signal strength. For an accurate identification of parameter, in this contribution we just consider a direct line of sight between the mobile station and base station. Now I want to go through some practical issues that we had in the experimental environment. First, we do not have any information about the antenna bore side angle and the electrical antenna down tilt. After several measurements, we found out the base station serves 3 cells, each covering 120 degrees, and one of the cells with an antenna bore side direction -30 is used for evaluation purposes. If you look at the figure, the antenna position is marked by a big circle at the origin. There is a chimney right next to the base station that may affect the measurements. This effect can be seen in the figure when X changes from 400 to 800 and Y is between -900 to -700. In this area, we should receive a high range of RSS according to direct line of sight. But as you can see, some part of measurements have low RSS values due to some obstacle like chimney. Buildings around base station location also cause some attenuations. Now we can see the result in experimental environments. In this scenario, vertical antenna gain effect is neglected. The contribution from the vertical antenna gain is expected to be smaller than 0.1 dBi under the assumption of nominal value of the parameters. As expected, the estimated effective horizontal antenna half-power beamwidth phi-h is wider than the nominal beamwidth due to scattering. Furthermore, the residual standard deviation of 7 dBm is in the expected range of 6 to 10 dBm. As a summary, I can say a semi-parametric model for RSS measurement is introduced that can be used to predict coverage in cellular radio networks. The model is composed of an empirical log distance model and a deterministic antenna gain model. Least square estimator is proposed to jointly estimate the path loss model and antenna gain model parameters. At the end, it's shown that the method can provide improved accuracy compared to conventional path loss based estimation methods. Thank you for your attention.
For more information about TRAX, please visit our site at trax.u20.nl.